So now we turn to chapter 4, theories for decision-making under risk in the behavioral spirit. And we start with section 4.1, prospect theory. I already told you it was the first one, but it's also still today the most important one, the most used, probably the most prominent theory. So we're not wasting our time discussing it. So I already said it was a new theory only for decision-making under risk, but it had much wider implications because it was the first one to get a theory of something behavioral. So irrational theory of irrational behavior. And I already showed you 2 citations in the past that people thought that was not possible. Here's a citation by Allais showing it. Let's not read it again. Let's immediately, Newton, he also said something similar before. He said, I can calculate the motion of heavenly bodies, but not the madness of people. And Kahneman and Tversky were the first. They could have said, well, we can calculate the madness of people. They were the first to show that it can be done. So here are some things, I already said it. So now we could have emotions, all kind of irrationalities, still quantitative predictions, because that's also typical of the behavioral approach and important. It's not just bashing the old theories, saying old theories don't work. But the thing is also constructive. They bring new theories and not just qualitative claims, but hard theory, quantitative predictions, the kind of things that the economists want and that we need. And that is what prospect theory did. And I'm going to explain to you now. It is, by the way, the second most cited paper that was ever published in the economic journal, at least some years ago. I haven't seen the most recent statistics of it. There was only one, it was a paper by White, and it had some small econometric technique. People are using it, they always cite him. So, in a way, maybe it's not fair, because the first paper with real substance, I think prospect theory, that was the most cited paper. So let us agree that we consider it the most cited paper ever. Let's make the rules of the game that way. Anyway, it gave the following formula, deviating from expected utility. It was a bit modest. They said we only know how to work for 2 outcomes. The rest we leave to later people. And here is a lottery with 2 outcomes, 2 non-zero outcomes. Yeah, 2 non-zero outcomes, most general they made claims about. And they said, roughly, we assume a formula of this kind. I say roughly, because I must say, small detail was a bit different, but we keep it simple. We look at this formula. Here, capital U, as before, is a utility function, or this sort of expected utility. Now it's important in prospect here, we scale utility to 0 equals 0. That's what we do. Then we sort out the 0 outcome. That's why it need not be written here. It has utility 0 anyhow, it doesn't count. So here we have the expected utility, but the probabilities, this W here, you see that you didn't see with expected utility. That's a probability weighting function. We now allow people to perceive probabilities or to weight. Maybe they perceive them right. Maybe they misperceive probabilities, and that's what W captures. But maybe it can also be they perceive them properly, but still they weigh them differently, maybe even deliberately do so. Anyway, probabilities turn into weights in a more general way than expected utility would have it. They can be transformed by the W function. That's the novelty of the one novelty of prospect theory, the one I'm showing you in the formula now. Of course, W satisfy W of 0 should be 0, of course. 0 probability doesn't happen, no weight. We take W of probability 1 equal to 1, that's just normalization. We just do it. Of course, the bigger probability, the bigger weight, strictly increasing. Natural condition for W we impose. The special case WP is P, then we get back the expected utility. By the way, this formula, strictly speaking, is for x1 different than x2. So 2 non-zero outcome. If there's only 1 non-zero outcome, then we can also, but then we just have to drop this part, or we say P2 is 0, so that this is 0. So that's how this formula is also handling 1 non-zero outcome, no non-zero outcome. So that's how it works. So this is often used in the literature for prospect theory. I already said a little bit, and there's a one nuance different, but we're going to make it easy on ourselves in this course. We can't be deep. So let's just stick with that formula for now. The biggest novelty, so one novelty you already saw, that's probability weighting. Prospect theory had another novelty, reference dependence, and I will not say much about it in the course. But the idea is that people when they evaluate outcomes, they don't take them just as they are, but they take some sort of reference point subconsciously, and they compare with the reference point. Things that are better than the reference point are gains. Things that are worse than the reference point are losses. And people trade gains quite differently psychologically than losses, so you have to make a big difference there, but classical theories don't do. And the reference point can move around, bring all kind of new phenomena. This was the biggest novelty of prospect theory, but we don't have very much time. This we will not discuss. We will simply assume that there's one fixed reference point, 0, and we will only look at gains, outcome better than 0. So that this interesting aspect, we have no time for it. We only focus on a novelty due to the probability weighting. Well, there have been many studies into this, empirical measurements. How do people perceive or weight probabilities? And the empirical studies say the prevailing shape is like this. It's inverse S-shaped. Small probabilities are overweighted, big probabilities are underweighted. This is the prevailing pattern. And this captures the psychology of risk attitude, how human beings feel about risk. That's quite not only the utility function, as expected utility does it, but also people have all kinds of feeling about probability. It's different between different people. This function is capturing. It's capturing how people feel about probability. If you want to have a realistic risk theory, you need to incorporate that. You need to think how people feel about probabilities to fit data well and all these things. And this is what prospect theory makes possible by introducing that function W. By the way, I already told you small probabilities are overweighted. That means that brings new empirical phenomena. For instance, it can bring risk seeking. And a common classic economic theory always said people always risk, well, of course, modular noise and all these things, but the prevailing pattern is really always risk aversion. And prospect theory says, no, wait a minute, that's not really completely the case. For small probability gains, as we will see, there is systematic risk seeking more than risk aversion. And I'll show you, do some calculation. Let's assume utility of x equal x to keep it simple. And for small money amounts, that is a reasonable assumption. And let us look here at the lottery, giving you x is probability p, otherwise 0. The formula is WPX. That's how prospect theory evaluates. But then you see, because it's small WP here is overweighted, WP is bigger than P. So this is bigger than P times X. It's bigger than the expected value. That means people like this lottery more than its expected value. This is risk seeking. That is what prospect theory predicts for small probability gains. A number of studies have confirmed this empirically. This is indeed what is happening. This explains why the gambling industry can be functioning and making a lot of money. If people play in a lottery, there's a 1 over a million probability that they get the main prize, but people don't understand how small 1 over a million is. They feel it maybe as 1 over 1,000. They're overweighting, overestimating the probability in some subconscious manner. That's why they don't understand that this lottery is not such a very good deal. That's why they overvalue it. That's why they're risk seeking. That's why a lot of people are participating in gambles and in lotteries. Insurance is in fact in a way the same phenomenon. The small insurance is also, so gambling is overweighting of small probabilities, but insurance is much the same. You know, maybe there's a very small probability of your house catching fire, but you don't understand how small that probability is. You just, oh, it may catch fire, oh. If it probably is 1 over a million, you feel it is 1 over 100 or so, and that's why you take insurance. So it's funny that insurance and gambling have the same basic psychological mechanism underlying it. Therefore, and this was a big success to popularize prospect theory can explain the coexistence of gambling and insurance. People insure their things, and at the same time they're playing, buying lotteries, they're playing in the gambling industry. These go together. One is a risk seeker, other is risk averse. Classical theories could not accommodate it, it was a puzzle to them. Prospect theory can explain it. Even more than that, it says it's basically the same phenomenon. So this surely in the beginning that helped popularize prospect theory, that it could do that. It can also accommodate the Allais paradox. Maybe you remember this paradox I showed before. I'm going to look into it. So the Allais paradox, with M denoting million euro, says in the upper choice people prefer left, in the lower choice people prefer right. I talk often with many students about this. I know also majority of students have these two preferences. I try to convince people that it's irrational, but it's not so easy. But anyway, we're now talking descriptively. Now you're talking how prospect theory can accommodate data. So I'm now I'm not trying to be normative. I told you normatively, rationally, I think expect utility is the right theory. Now I'm explaining prospect theory to you. In my view, this is useful for empirical work, not normative. Other people disagree. That's my view. Anyway, so prospect theory can accommodate the Allais paradox. And for instance, let's give some plausible reasons. Let's assume that utility of 10 million is 3/4 utility of 40 million. So it's surely not linear. Of course, utility of 40 million is more than utility of 10 million, but it's not so very, maybe it's 1/4 more or so. This is a reasonable assumption for many people. In that case, if you look at the first preference, if the weight of probability 0.8 is less than 3/4, then already we get this preference. So then this is less than 3/4 times utility of 40 million. That's less than utility of 10 million. First preference is accommodated. And as I told you, this is very reasonable, So the common shape here, I put it again, the big probability are greatly underweighted. Yeah, it's a common finding. W of 0.8 is smaller than 0.75. So this is working well. If we look at the second preference, then the utility ratio is again 3 to 4. But now, if you look at the figure, well, if the weighting function were linear, then this ratio would be 0.8. In reality, you see that in this region, the weighting function is concave, so that ratio is bigger than 0.8. So it should be bigger than 0.75. If you do the algebra with the ratio, you see that that's already enough to accommodate the second preference. So you see that with the common empirical findings, the Allais paradox is easily accommodated. And that was also a success for prospect theory because this Allais paradox was really famous and they could accommodate, explain it. So good. I'm gonna continue a bit how prospect theory accommodates Allais. I want to do some more quantitative, you already saw now that it works, but I want to elaborate a bit more with quantitative calculations because it's good to do anyhow. And I'm going to assume a utility function like this, a power function, constant relative risk aversion, people say, and that parameter, I'm going to take that value. Then indeed, we have exactly this ratio. This is for these big amounts, it's plausible. Maybe some of you had courses already with relative risk aversion. I wrote the index, risk aversion index for relative risk aversion. Those of you who heard about it know that here this index is that number. So several of you had courses with it, but if you never heard of it, never mind, can ignore it. Anyway, this is the utility function that we assume. And we assume this probability weighting function, parameter gamma is 0.61. That was the probability weighting curve that you saw a moment ago, which is empirically quite good, okay? Now, before I go into calculations, I want to tell you something else, and that is in many situations, if you do calculations, it is really useful to calculate certainty equivalents of lotteries. For instance, if you calculate the expected utility of the lottery or the prospect theory value of a lottery, you get some number, you don't know so very well what does it mean, or expected yield 0.734, what does it mean? It depends on how you scale it, you don't know. But certainty equivalent, if you say this gamble is equivalent to getting €100 for sure, then you know exactly what it means. In many situations, this quantity is a very useful quantity to get insights and to do calculations with. So we will do that. So if we have a prospect and the prospect theory value is OPT, then the certainty equivalent must be equally good. And this is the prospect theory value of that certainty equivalent. So the utility of the certainty equivalent must be OPT. That means the certainty equivalent must be the U inverse of OPT. So in general, if you calculate certainty equivalence, first you calculate the functional value of the prospect, then you take the U inverse and you have the certainty equivalent. So that's what we'll be doing a lot. Now there's the probability weighting function again. Here I put the two preferences of Allais paradox. Now I want to do a few calculations with what I showed to you before. First of all, the first lottery is 10 million for sure. The prospect theory value is 28.3. If you calculate, that's just the number. So the certainty equivalent is the U inverse, that's 10 million. Well, that's trivial, of course. You know, the certainty equivalent of 10 million is 10 million. But anyway, that's what it is. Now we go to the second lottery, that one. Then on the prospect theory, that will be smaller, as we will see, because that is the weight of 0.8 times utility 40 million and utility 0.0, so I need not write the term of that. The weight here is 0.61, the utility, that very concave utility function, give that number. So this is a prospect theory value that will not mean very much to you, just like that. But then we calculate certainty equivalence, we take the utility inverse, then we get the number that tells us more. We see here getting 3.62 million for sure is equivalent to that lottery. Maybe you think, wait a minute, this is 40 million, this is 3.6 million, so quite smaller, but still getting such an amount for sure is really nice. So it's empirically quite plausible that people have this certainty equivalent. I can already say that in these calculations, pessimism is that people underweight the probabilities. If the probability is a 0.8, people take it as 0.61. That makes them too pessimistic. So they often use the term pessimism to describe that aspect of the probability weighting function. And I'm going to continue the calculation, but before, maybe a general remark, that is, I told you already in the beginning, the behavioral approach brings in mathematical psychology into economics. And if you really want to understand these models, and I'm also doing these calculations to make that happen, it's really nice if you can see in the formulas and the calculations what kind of psychology of the human mind they are capturing. So if you see these calculations, if you think, oh, numbers, well, then it doesn't help you much. But if you can see, wait a minute, people are very pessimistic. That's happening here. They are underestimating probabilities very much. And that adds to why this number is going to be quite low. People are going to be quite pessimistic about this probability, and already quite small sure amount is equivalent. Pessimism is working here and is pushing down the certainty equivalent. So if you recognize your pessimist, people are a bit too afraid of probabilities, that's happening here. And if like that, if in all the formulas you recognize this psychology of human beings that is captured by this formula, then you really understand the theories. So I hope that these calculations that I show you help in that way to get better feeling of what these theories do. I continue the calculations. The prospect theory value of this prospect is W.25 times utility of 10 million. And you see the W.25, not much is happening, maybe a little bit overweighting or quite neutral. This is not bringing strong optimism or pessimism, but utility is very concave. So it turns out that getting 8.25 million for sure is equally good as that lottery. Well, it's plausible. So the certainty equivalent, sorry, I made a blunder. This is the prospect theory value, not at all. The certainty equivalent is the U inverse of it, and that's this amount of money. That's quite less than 1 million. That's how it is. So this small, maybe quite small amount of money for sure is already equally good as that lottery. That's how it is. And this is smaller than if we calculate the prospect theory value of that last lottery here. The prospect theory value of W.20 is 0.26, a bit overweighted even. A little bit of optimism is happening here. Utility is very concave. So we get this number, certainty equivalent turns out to be 0.061 million. So this money amount is equally good as that lottery. We see it's the certainty equivalent here is a bit bigger, quite bigger than here. So people rather have the low lottery than the high lottery. And you see here this extra psychological component that prospect theory brings in relative to expected utility probability weighting is in fact not doing very much in this choice. Here it's simply 40 million is so much more than 10 million that people prefer the lower lottery, and that's just how it is. But here in the upper choice, we see pessimism is hitting strongly on the lower lottery, but it's not at all hitting on the upper lottery. So in that sense, this psychological effect is benefiting, the upper lottery is privileged relative to the lower lottery here. And that's why here the preference reverses relative to the low situation. Here they prefer the 10 million, here they prefer the 40 million option. So that's how it works. And that is how prospect theory and probability weighting and all the psychology coming with it accommodate and in a realistic manner accommodate the empirical findings. Maybe I should also say that in these behavioral theories, it's quite good that what we do in these theories is capturing really the human psychology. This is really going on in the minds of people. They are too pessimistic about probabilities. This W function captures things going on in the brains of people. So that helps. It's not just an as if modeling. We are more ambitious than that in the behavioral approach. And we think that's why this is working well. Anyway, this original prospect theory in 17, there were some problems still. The formula is quite good already, and they were the first to bring formulas that could do anything. They were not perfect. There were some, and also never a behavioral foundation was really given. So that might have been a signal that there's a problem. You always like the ordinalists emphasize, and I agree with them, a behavioral foundation is good, and you know what it means. We're going to do behavioral, but we surely want to have behavioral foundations. All the good things that we learned from the ordinalists we want to keep. For original prospect theory, from the first one, people never really had a behavioral foundation, and that could already have been a signal that maybe not the best perfect in every respect. For instance, if there are many, I gave you the formula only for 2 outcomes, and Kahneman's first key were modest, they did not claim more. But any extension to many outcomes that people tried did not work well. Too much overweighting always. It also turned out people discovered, some later mathematicians discovered, that this formula violates stochastic dominance. Stochastic dominance means if you have a lottery and you improve an outcome, it becomes better. The more money, the better. It turns out that this formula always sometimes, I have no time to explain it now, but it was discovered. That's really, I know sometimes everything happens in reality. There are empirical situations in which people violate stochastic dominance, but not in the way that this formula says. This is also, of course, rationally speaking, this can never be, but also empirically, what this formula is doing is not really how it should be. So people knew it's quite a good, it was the first theory that can do anything at all. But it was quite quickly clear we will need improvements of that theory to get real good work. And those will come a bit later. Cumulative prospect theory, quick-in idea comes soon. That was the situation of prospect theory, how it started. Then in 1983 came the next risk theory. Next well known, there was one actually quick was earlier, but was not well known. But so for a while, this was the first theory to 1983, and he did give a behavioral foundation. So in that sense, it was a novelty, his weighted utility. That is what I'm going to explain next, but that will be in the next recording. So this recording will finish.